Okay, we finished our discussion about how to prepare buffers. And now the next question comes up. What happens to a buffer when we dilute it? If we dilute the buffer, what happens to the pH? And I sort of talked about this a little bit on the board last time, looking at what happens to the pH and how the pH is affected. We know from the Henderson-Hasselbalch equation that pH is equal to pKa plus the log of the concentration of A minus over the concentration of HA. And if we think about this, the pKa for a particular material does not change. So this ratio is added on to the pKa value, so that's really what controls the buffer and the pH of the buffer. So what happens if I dilute a solution? What happens to the pH? If I dilute the solution, don't I dilute the whole solution? So I'm diluting A minus concentration, and I'm diluting the HA concentration. So how is that going to change the pH? It's going to do what? It's going to make it closer to 7? Say it again, Ethan. It doesn't change at all. Okay, how does it affect it? It doesn't. Because think about it. Let's just say I had this was 2 molar to 1 molar, okay? So the ratio is 2 to 1. So we would take the log of 2 and we would add that on. Now what if I diluted this and it now is 1 to 0.5? What's the ratio? 2 to 1. So it's log of 2, so it doesn't change. Christopher?
That doesn't make intuitive sense, though.
Yeah, it does. Well, okay, sorry, why not?
It's the opposite log of the hydrogen concentration.
No. It's not. I mean, we do say pH is the negative log of hydrogen concentration. But in a buffer, remember that the hydrogen concentration and the A minus concentration are both contributing to the pH. In an acid, where you have the hydrogen ion is only coming from the acid, the H plus and the A minus are the same. But when you have a buffer, they're not the same. So that changes things. So we know in a weak acid, we've got HA is in equilibrium with H plus A minus, right? And we find the pH. We have some starting concentration. So we have Ka is equal to H plus times A minus divided by HA. And we can rearrange this to say that the hydrogen ion concentration is equal to Ka times HA divided by A minus. So even here, the hydrogen concentration is dependent on what the A minus and the HA are. So if the A minus changes, the H plus is going to change. And in a buffer, we have put some A minus in there from another source. And all we've done now is take this equation and represent it logarithmically here, because I've taken the negative log of this whole equation. So the pH is dependent on what the acid is, what its pKa is, and the ratio of A minus to HA. If you have an acid and it's a 1-to-1 ratio here, then your pH is equal to your pKa. I don't think that's answering your question, is it?
Well, the way I'm thinking of what's in my beaker right now.
Okay.
And I see there's an equilibrium moving back and forth, but in general, overall, there's a fixed amount of hydrogen ion.
Yes.
And so if I add in, say, pure water, then that number of moles of hydrogen ion per liter becomes hydrogen ion, or number of moles of hydrogen ion per a greater number of liters, which would decrease the hydrogen.
Oh, I understand what you're saying. You're saying that if I have 1 molar hydrogen ion and I dilute it 50-50, now I'll have a half molar hydrogen ion, and the pH would change. And that's correct. That's if you have loose hydrogen ion. If you have a strong acid, you're absolutely correct, if it's a strong acid. If you have a strong acid where everything is dissociated and you have just loose acid because you've got like hydrochloric acid, so you got hydrogen ions and chloride ions. If you dilute that, the pH changes, absolutely. But this is not a strong acid. This is a buffer where you have equilibrium going forward and backwards. So you're making hydrogen ion and you're using up hydrogen ion. And because in the weak acid, the hydrogen ion depends on the concentration of the acid to start with and how much is ionized.
Certainly there's only so much hydrogen ion that can be made.
True, because you only have so much acid. But do you see that looking at this, the hydrogen ion is dependent on this ratio?
Yes, mathematically.
So mathematically, if you dilute this, the ratio stays the same. Ka is a constant, right?
Yes.
So the hydrogen ion concentration is equal to Ka, which is a constant, times this ratio. Now, if I dilute the whole thing, I'm diluting both of these the same way, right? So the ratio doesn't change, does it? So the hydrogen concentration doesn't change in a buffer. A buffer and an acid are not the same. If you just dilute the acid, you will change the pH. But if you dilute a buffer, the job of the buffer is to maintain a steady pH and to avoid changes in pH. And we're going to do some problems where we see how that works. Yes?
Oh, yeah, that was my next question. What if the dilution or the dilute that we're adding is not water?
Well, then you're not diluting it. Then you're adding something else and doing chemistry.
And we're going to do that.
Okay? Diluting means that you just add more solvent. That's what dilution means. If you add HCl, that is not diluting it. That is adding a strong acid. Then you're doing some chemistry. Okay? Okay, so we had introduced the Henderson-Hasselbalch equation, and we used this to figure out what the ratio should be to have some, to be able to calculate how to prepare a buffer. So now we can also use this to calculate pH. So let's look at this example. We did this problem previously on page 17.4 in the notes, and we set this up in an ice chart. This was the first problem we did with a buffer. And we said that the thing that was different is that we had an initial concentration under A- in our chart. So we've done lots of calculations with the chart. Now we can actually calculate the pH of a buffer using the Henderson-Hasselbalch equation also. So we know pH is equal to pKa plus the log of A- over HA. So this is an acetic acid solution and a sodium acetate solution. So we look up the pKa for acetic acid. It's 4.74 plus the log of the salt concentration. Now the A-, remember, gets into solution with some cation that makes it soluble. So the sodium acetate, this is sodium's a +1 and acetate's a -1, so it's 1:1. So I have 0.015 molar sodium acetate divided by the acetic acid concentration, 0.10 molar acetic acid. So my pH is 4.74 plus the log of 0.15. So pH is 4.74 plus a negative 0.82. So that is equal to 3.92. And if you go back, flip back to your notes on page 17-4, you will see this is exactly the same answer we got when we calculated this using an ice chart. So if you look at this, here it is on top using an ice chart, and here we get the same answer using the Henderson-Hasselbalch equation. So you can decide which you like better. I like the equation a lot of times. It's just faster for me. So when you have a buffer, anytime you have a buffer, you can use the Henderson-Hasselbalch equation, or you can use the ice chart. If you're so comfortable with the ice charts now, then it's okay to use that too. Okay, now I didn't put one in here for you to try because we're going to look at some with basic buffers also.